Imagine a world where computers can solve problems in seconds that would take today's fastest supercomputers thousands of years. This isn't science fiction, it's the promise of quantum computing. We're standing at the threshold of a technological revolution. It's as big as the invention of the internet, maybe even bigger. Think about your smartphone. It's millions of times more powerful than the computers that sent humans to the moon. Now, quantum computers promise to make our current tech look like stone tools. They're not just faster, they're a whole new way of processing information. It's like comparing a bicycle to a spaceship. But what makes quantum computers so special? It's all about how they handle information. Regular computers use bits, tiny switches that can be either on or off. Quantum computers use something called qubits. These can be on, off, or both at the same time. It's like having a light switch that can be up, down, or somehow both up and down simultaneously. It's weird, it's wild, and it's about to change everything. Let's talk about qubits. They're the heart and soul of quantum computers. Think of them as the quantum version of regular computer bits. But while bits are like coins that can only be heads or tails, qubits are like spinning coins. They're heads, tails, and everything in between all at once. Imagine you're playing a game of 20 questions. With regular bits, each question eliminates half the possibilities. With qubits, it's like asking all 20 questions at once. You get all the answers simultaneously. That's the power of qubits. They can process vast amounts of information in parallel. But qubits are fragile. The slightest disturbance, a stray magnetic field, a tiny vibration, can make them lose their quantum properties. Creating and controlling qubits is one of the biggest challenges in quantum computing. Scientists are using everything from superconducting circuits to trapped ions to diamond defects. Now let's dive into superposition. It's one of the weirdest and most powerful features of quantum mechanics. In our everyday world, things are either one way or another. A light is on or off, a door is open or closed. But in the quantum world, things can be in multiple states at once. Think of it like this. Imagine you have a coin in a box. You shake the box and the coin is flipping. While it's flipping, is it heads or tails? In a way, it's both. That's kind of what superposition is like. A qubit in superposition is like that flipping coin. It's in all possible states at once. With superposition, quantum computers can explore multiple solutions to a problem simultaneously. It's like being able to take every possible path through a maze at the same time. The art of quantum computing is manipulating these qubits and extracting useful information before they collapse. Now we come to entanglement. Einstein called it spooky action at a distance. It's when two or more qubits become connected in such a way that the state of one instantly affects the other, no matter how far apart they are. It's like having two coins that always land on opposite sides, even if they're on different planets. Imagine you and a friend each have a magic 8-ball. Whenever you shake yours, your friend gives the opposite answer instantly, even if they're on the other side of the world. That's kind of what entanglement is like. It seems to violate everything we know about cause and effect. But in the quantum world, it's business as usual. Entanglement is what gives quantum computers their incredible power. It allows qubits to work together in ways that classical bits can't. It's like having a team of psychic superheroes who can instantly share information and coordinate their actions across vast distances. But entanglement is also incredibly delicate. The slightest interaction with the outside world can break it. Section 5. Classical versus quantum, a tale of two computers. Let's compare classical and quantum computers. It's not just about speed, it's a fundamental difference in how they process information. Classical computers are like solving a maze by trying one path at a time. Quantum computers are like water flowing through the maze, finding all possible paths simultaneously. Classical computers use bits that are either 0 or 1. It's like having a bunch of light switches that are either on or off. Quantum computers use qubits that can be 0, 1, or both at the same time. This difference means quantum computers excel at certain types of problems. They're great at simulating quantum systems, like molecules for new drugs. They can factor large numbers much faster, which has huge implications for cryptography. And they can optimize complex systems in ways classical computers can't. But quantum computers aren't better at everything. Quantum and classical computers will likely work together, each doing what it does best. Section 6. Cracking codes, quantum cryptography. One of the most talked about applications of quantum computing is in cryptography. Our current encryption methods rely on the fact that it's really hard for classical computers to factor large numbers, but quantum computers could crack these codes like a hot knife through butter. This might sound scary, and it is in a way. Much of our digital security relies on these hard-to-crack codes. But quantum computing isn't just about breaking codes, it's also about making unbreakable ones. Quantum cryptography uses the principles of quantum mechanics to create codes that are theoretically impossible to crack. Imagine a lock that changes if anyone even looks at it. That's kind of what quantum cryptography is like. Some banks and governments are already using quantum cryptography for their most sensitive communications. As quantum computers become more powerful, we'll likely see a shift towards quantum-safe encryption methods. Section 7. Artificial intelligence gets a quantum boost. Artificial intelligence and quantum computing are a match made in tech heaven. AI is all about recognizing patterns in vast amounts of data. Quantum computers are great at processing vast amounts of data in parallel. Put them together, and you've got a recipe for some serious brainpower. Imagine an AI that could analyze every possible move in a game of chess simultaneously. Or one that could simulate complex molecular interactions to design new materials or drugs. Quantum AI could do all this and more. It's like giving a supercomputer a superpower.
One area where quantum AI could shine is in machine learning. Classical computers struggle with certain types of machine learning problems, but quantum computers could potentially solve these problems much more efficiently. It's like teaching a computer to recognize cats in pictures, but at the speed of light. It's opening up whole new realms of possibility in AI research.
Section 8. Revolutionizing drug discovery. One of the most exciting applications of quantum computing is in drug discovery. Designing new drugs is incredibly complex. You need to simulate how molecules interact with each other. This is exactly the kind of problem quantum computers excel at.
Classical computers struggle to simulate even relatively simple molecules, but quantum computers could potentially simulate complex molecular interactions with ease. It's like the difference between trying to model ocean currents with a bathtub versus an actual ocean.
This could dramatically speed up the drug discovery process. Instead of spending years and billions of dollars testing countless compounds, researchers could use quantum computers to identify the most promising candidates much more quickly. It's like having a crystal ball that shows you which drugs are most likely to work. Section 9. Real-world quantum computing in action. Quantum computing isn't just theoretical, it's already being used in the real world. Companies like IBM, Google, and D-Wave are offering cloud-based quantum computing services. Researchers and businesses can access these quantum computers to solve real-world problems. For example, Volkswagen used a quantum computer to optimize traffic flow in Lisbon. The computer analyzed data from 26,000 taxis to figure out the best routes. It's like having a traffic control system that can predict and prevent jams before they happen. In finance, Goldman Sachs and JP Morgan Chase are exploring quantum computing for risk analysis and trading strategies. Quantum computers could potentially analyze market data and make trading decisions faster than any human or classical computer. Even in areas like climate modeling, quantum computing is making waves. Section 10. Expert insights, voices from the quantum frontier. Let's hear from some experts in the field.
Quantum computing is a new paradigm, a new way of processing information that could lead to exponential speedups for certain problems. It's like discovering a new continent of computational possibility. Quantum computing has the potential to solve problems that are intractable for classical computers, but we're still in the early stages. It's like we've invented the airplane, but we're still figuring out how to fly across the ocean. Our experiment achieved quantum supremacy, performing a computation in 200 seconds that would take a state-of-the-art supercomputer 10,000 years. It's like breaking the sound barrier of computing.
We are still far from practical quantum computers. There are significant engineering challenges to overcome. It's a reminder that we are pioneers in a new frontier. There's still much to discover and overcome.
Section 11. The quantum future. What lies ahead? As we look to the future, the potential of quantum computing is both exciting and daunting. We're on the brink of a new era in technology, one that could revolutionize fields from medicine to finance to artificial intelligence. It's like standing at the dawn of the digital age, knowing that computers will change everything but not quite sure how. But with great power comes great responsibility. Quantum computers could break current encryption methods, potentially compromising digital security. They could also be used to create incredibly complex simulations, for good or ill. It's crucial that we develop quantum technology responsibly, with careful consideration of its ethical implications. Education will be key. We need to train a new generation of quantum engineers and scientists. We also need to educate the public about quantum computing, its potential and its limitations. As we stand on this quantum frontier, one thing is clear: the future is going to be very different from the past. The quantum age is about to begin,